So who is so who is 5x? I think I didn't see you earlier in the class. So Anushika, you are joining for the first time or you joined the earlier sessions?
So first time.
Can you please introduce yourself? I mean, where are you
I'm
from?
Anushika Yadav and I'm from Delhi, sir.
Okay,
I have
okay.
done my post graduation in 2022.
From where? From which
Sorry,
university?
sir.
From which university you have
Sir,
come?
it's
Yeah.
private university, sir. It's in Gurugram, HT University.
Oh, okay, okay. Okay, fine. So you are applying for GATE this year. I mean, after I think in the next month.
Yes, sir.
Okay.
Yes, sir.
Yeah, yeah. Okay. Okay. I think I can start. Later on, people will join. Okay. Just give me 1 minute. Okay. Okay. I am sharing my screen. Is my screen visible? Can you confirm?
Yes, sir.
Okay. 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 I'm starting with the first question of this class. Just okay. Fine. So this is the question from GATE Physics 2015. This question was also sent by Harish. I think Harish is not there today, but he wanted me to discuss this question. And this question also was asked in the GATE Physics paper 2015. This is a numerical answer type question of 2 marks, and this is from quantum mechanics. The question is let the Hamiltonian for two spin half particles of equal masses m, momenta p1 and p2, and positions r1 and r2 in 3 dimension. B. The Hamiltonian H equals to 1 by 2m p1 square plus 1 by 2m p2 square plus half m omega square times r1 square plus r2 square plus k times sigma 1 dot sigma 2 vector, where sigma 1 vector and sigma 2 vector denote the corresponding Pauli matrices with H omega equals to 0.1 electron volt and K equals to, here K is a constant in this Hamiltonian, that is 0.2 electron volt. If the ground state has net spin 0, then the energy in electron volt is, so basically you have to find the ground state energy with these values. Is the question is clear to everyone? Any confusion about the question?
Sir, can you read it again?
You want me to read it again? Okay. I mean, the question is okay. Uh, the question is, let the Hamiltonian for two spin half particles of equal masses m, momenta p1 and p2 vectors, and positions r1 and r2 vectors. B, the Hamiltonian H equals to 1 by 2m times p1 square plus 1 by 2m times p2 square plus one half of m omega square times r1 square plus r2 square plus k times sigma 1 vector dot sigma 2 vector, where sigma 1 vector and sigma 2 vector denote the corresponding Pauli matrices. And here it is given also h cut omega, that is related to the harmonic oscillator potential. You can see there is two terms, one is spin term and another part of Hamiltonian is basically related to three-dimensional quantum harmonic oscillator. That energy scale h cut omega is 0.1 electron volt, and the constant k in the spin part, it is 0.2 electron volt. So if the ground state has net spin 0, then the energy in electron volt is, so basically you have to find the ground state energy with this Hamiltonian of this system. Any doubt, Amit?
No, sir.
Okay. Okay. So try to find the energy value with this Hamiltonian and then apply the ground state condition to find the energy. And also you are given the h cut omega and k values. And also this question is related to spin half particles. So your spin is half the spin eigenvalue, if you want to say. Okay, just let me check who joined this class. Okay. Okay. Uh, can you say how to approach this problem? Any idea? Or do you want to think? You can take time, then you can share your thoughts. So the question is clear to everyone, right? Any doubts? Please ask me first. So Amit, are you trying?
Yes, sir. Just confused about how to deal with the perturbation term.
Perturbation term, okay.
It's the K sigma 1 dot sigma 2.
There is nothing to do with the perturbation, Amit. It's simple Hamiltonian. You have to just find the energy eigenvalue. There is no perturbation involved in this. So, right? How, I mean, did you encounter in the spin? The spin chapter in quantum mechanics, how to deal with this dot product of sigma or spin? How to? I mean, this is a, I think, common thing when you.
Yes, I just don't remember it right
Oh,
now.
okay, okay, okay.
Means
Anyone? How to? Sorry.
we can separate the first
Hmm.
two terms, write it as H1 plus H2, like
Right.
two simple hydrogen atom Hamiltonian, and then simply
Not
put
hydrogen
their
atom. This is a quantum harmonic oscillator.
okay, yes,
Not
yes,
hydrogen atom.
one plus half
The
means
potential is
three.
harmonic oscillator potential here. You can easily identify this, right? Half m omega
Yes,
square r square. So that's correct. So the third part will be spin part. Basically, there are
yes,
three Hamiltonian involved in this. Two is 3D quantum harmonic oscillator, and last one is your spin part. And the spin is in the form is dot product of two spin half particles. Yeah. So anyone can even say how to deal with this part, because you can't directly tell what will be the energy eigenvalue of this dot product. So how to deal with this? Anyone can try? Okay, I'll wait for another 1 2 minutes. Let me see. Joined. So Harish is here? No, I think Harish is not here today. Okay. So anyone wants to try for some time, or I will discuss the solution part?
so if you can give some hint about the
Okay.
third part.
Okay. So so there's two spins. So basically, the eigenvalue of what I can say. If you apply the operator a square or sigma square on some spin state, what will you get? Can you even tell? You know about the angular momentum, right? L square. So what will you get then? What's the eigenvalue of if you apply L square operator on some state of spin angular momentum or angular momentum state? That is L into L plus 1 times h cut square, right?
Yes, yes,
Right, right. So you
yes,
yes. So but only L operator you can't say. Right, you can say, but not in an easy way. So you know that information every time. If you operate L square or S square operator, you will get S into S plus 1 times h cut square, right? Am I clear?
yes, sir.
Okay. So now here, though, you have two spins, so you have to convert in such a way you get in terms of square of them. How will you apply that thing? What's the first thing come into your mind when you have two spins sigma 1 sigma 2, and some total spin is sigma equals to sigma 1 plus sigma 2, right? Total spin is sigma 1 plus sigma
We
2.
can We
Huh?
can do it like this sigma 1 plus sigma 2 whole thing square, and
Yes.
from then we can get sigma 1
Yes.
dot sigma 2.
Yes. Then just substitute that, because sigma equals to sigma 1 plus sigma 2, where sigma is the total spin of your system, right? Then square it
Yes.
both side, then find the dot product in terms of square term. Then you can easily tell the things, right? Just apply that. I mean, this is the hint. I think after that you can do. Here total spin is given 0, so your sigma will be 0, and sigma 1, so you know, right? Half spin particle, so what will be, right? Hmm, okay. Okay, so anyone else, then, I mean, apart from Amit, anyone else is trying these things? Amit, so now,
Yes, I'm trying.
okay, okay. So let me summarize the hints of this question. So basically, just give me a minute. Okay. So in this Hamiltonian of two spin half particles, there are three parts. If you can segregate them. So one is P1 square by 2m plus half omega square R1 square. These two things will give
Sir, is
you.
it zero?
No, it's not 0. Please look into it properly. Okay, please try it. I will ask. Okay, I will ask everyone. I mean, how? Okay, fine. So there are three parts. First part is P1 square by 2m plus half m omega square R1 square. This will give you a 3D quantum harmonic oscillator for first spin half particle, and then another 3 dimensional quantum harmonic oscillator for the another spin half particle, that is P2 square by 2m plus half m omega square R2 square. So we have two 3 dimensional spin harmonic, quantum harmonic oscillator here, and the third term in the harmonic oscillator is the spin interaction term within these two spin half particle. So first two term you know already from your basic quantum physics, you have studied what will be the energy eigenvalue for 3 dimensional quantum harmonic oscillator. But third term you have to do some mathematics in there to get the energy eigenvalue for this third term. Then you have to add up the three energy eigenvalues, and here it is given the condition, also values the each cut omega, and here k value this constant, and also for ground state spin 0. That means if your total spin will be sigma 1 plus sigma 2, right? So sigma 1 plus sigma 2 is 0 for ground state, and for spin half particle, you know, right, how to what will be your sigma 1 square and sigma 2 square, right? Amit has already told that you have how we have to deal with this thing, this sigma 1 dot sigma 2. So you have to just apply sigma equals to sigma 1 plus sigma 2, then square both side. So you will get sigma square equals to sigma 1 square plus sigma 2 square plus 2 sigma 1 dot sigma 2. Then you can substitute the sigma 1 dot sigma 2 in terms of sigma square, sigma 1 square, and sigma 2 square. Then apply the formula, that sigma square, or you can write it in the terms of s square, because s is equal to h cut by 2 sigma. Pauli matrix this relation. So if you apply the s square in on some spin state, then you will get s into s plus 1 h cut square, right? Then your total spin will be 0, that S and S1 and S2 is your half because your spin half particle. That's it. You will get the total energy eigenvalue of the system and then apply these values, you will get the answer. So, that is the total procedure. What I will be discussing in the solution, that is the procedure I will follow. So, Amit, you want to take some 1-2 minutes or I will go to the solution? So, who told me 0 that answer?
So minus 0.3.
Who is this?
So Amit.
Yeah, that's correct. That's minus 0.3. Okay. So, can you share your solution? I mean, you can tell how you got into the answer. Share with everyone.
So the handwriting is too bad. I just did means I took P1 square by twice m plus half m omega square R1 square separate. So its energy eigenvalue would be N1 plus 3 by 2 h cut omega, since it is three-dimensional
Hmm.
quantum harmonic oscillator.
Hmm.
Similarly, for the second part, I can write it as the energy eigenvalue as N2 plus 3 by 2 h cut omega.
Hmm.
Then I just followed what you said about the sigma part, and for its the energy eigenvalue is coming as 2k times s into s plus 1
Hmm.
uh, minus s1 into s1 plus 1 minus s2 into s2 plus 1, and
Hmm.
then s1 and s2 are half and s equals to 0, and
Right.
then we just
Um,
get the values.
and also for N1 and N2 it will be 0 for ground state, right? Yeah, for 3D harmonic
Yes.
oscillator. Yeah. Yeah, that's the simple thing. Okay, I will anyway. I will be discussing the solution. Amit, you are correct. Okay, so I will go to the solution part. Okay. Mm, okay. So, this thing is given already that Hamiltonian is P1 square by 2m plus P2 square by 2m plus half m omega square times R1 square plus R2 square plus k times sigma 1 dot sigma 2. So, here sigma 1 and sigma 2 denotes the corresponding Pauli matrices that is related to the spin half particles. So, here only concerned thing is your spin part, because apart from that you know what you have to do. So, we are worried about this term only first, k times sigma 1 dot sigma 2. So, what we will do, the total spin sigma equals to sigma 1 plus sigma 2. So, we will take the dot product with sigma both side, or you can take the square, that is the same thing. So, it will give sigma square times sigma 1 square plus sigma 2 square plus 2 sigma 1 dot sigma 2. So, from here you can get sigma 1 dot sigma 2 equals to half of sigma square minus sigma 1 square minus sigma 2 square, right. Now, we will rearrange the Hamiltonian, the terms in the Hamiltonian, that is P1 square by 2m plus half m omega square R1 square, that is the momentum and spatial part of these first spin half particle, and second the same thing, the spatial and momentum term of the second spin half particle, and the third term is the spin interaction, that we have substituted the dot product with this kind of thing for ease of calculation. Okay. So, you can do this thing what I have done here. So, I have just converted the sigma into S for my convenience. Anyway, you can deal with this sigma directly, that does not matter. So, you know that S equals to h cut by 2 times the Pauli matrix. So, I have just multiplied the 2 by h cut square whole square and I have just written it as S square minus S1 square minus S2 square. Okay. So, effectively what we are getting, this H1 plus H2, there is a 3D quantum harmonic oscillator, and this is the 2k by h cut square times S square minus S1 square minus S2 square. Here, okay, then this H1 and H2 is basically your N1 plus 3 by 2 times h cut omega plus N2 plus 3 by 2 times h cut omega, and this will give you the energy eigenvalue 2k times. So here you will get s into s plus 1 plus times h cut square. So h cut square from all the terms will cancel out this h cut square. So I have not written it here. So this will give s into s plus 1 minus s1 into s1 plus 1 and minus s2 into s2 plus 1. Okay, fine. Up to this everything is clear, right? I mean, any doubt about this? Anything?
Sir,
Yeah, who's this?
Sir Prajwal.
Yeah. Please tell me.
Sir, why you substituted sigma values? Sigma means you converted sigma into S, no? So we
Doesn't,
can do it.
you can do it. I mean, it doesn't matter. It doesn't matter. You can do it directly.
Sir, but
Yeah.
the term is not coming in that
What term is not coming
2
there?
by h cut, 2 by h cut
2y h card. What is that?
square.
Sorry, I didn't get you. Can you please
Uh,
clear your question?
Sir, what I did was when he
Mm-hmm.
said no, that square we will just expand it and get it. So I just converted sigma into s there itself,
Oh,
and
you have written sigma 1
uh,
square, that sigma 1 times sigma 1 plus 1.
uh, no, sir, means I put sigma value into s in that equation itself,
In the
like 0 equal to s1 square plus s2 square.
so you will get S1, okay. Then you will get S1 dot S2 equals to minus of
So
half.
by that thing we will end up with S1 dot S2 something like that.
So what's
Uh,
the problem there? I didn't understand the problem.
Okay. I
No, no, no. You can,
I got it.
tell your problem. That's not. Maybe I am not understanding properly, but you can try. I mean, you can say so that I can understand the problem. I mean,
No, sir. Actually, I converted into s in that equation itself, and then I forgot to take that s values in there.
oh,
I
okay.
directly took it.
But because this is very simple, there is nothing tricky in these things. You can directly deal with the sigma 1 also or s also. That doesn't matter. I mean, because we eventually deal with s spin operator, so that's why for my convenience I converted into s. That's the thing here. Nothing new in it. Okay. Okay. Anyone else? Any doubt about this final energy eigenvalue? This expression? I think it should be clear. Okay, I am going to the last slide. So now we will go for the final result. So in the ground state for the 3-dimensional harmonic oscillator, so basically I have written here N1 and N2. So basically as it is 3-dimensional harmonic oscillator, there will be 3 quantum numbers, principal quantum number Nx, N plus Ny plus Nz, right. So sum of that I have written it N1 and for also the second electron, the second spin half particle N2. So there are basically 3 terms involved in this N1 and 3 terms involved in this N2. For the ground state, you have to consider the set 0 comma 0 comma 0 for nx, n1, nz for both the cases. So basically the sum will give you n1 equals to 0 and n2 equals to 0. So for that I have chosen that n1 equals to n2 equals to 0 and total spin here is equals to 0, that is given in the question, ground state, right. So that is 0 and s1 s2 is the spin half particle, the spin of the spin half particle, right. So that will be half. So just apply that values. So you will get 3 by 2 h cut omega plus 3 by 2 h cut omega plus 2k times 0 for the ground state is equal to 0 minus half into half plus 1 minus half into half plus 1. So it will give you 3 h cut omega plus 2k times minus 3 by 4 minus 3 by 4. So this will basically give you minus 3k. Now you are given each cut omega I think 0.1 and k equals to 0.2, right. Just put that. So you will get 0.3 minus 0.6, that will give you minus 0.3 electron. So your ground state energy for this system with this Hamiltonian will be 0.3 electron. Is it clear? Any doubt?
yes, sir.
Okay. So I want everyone to involve or participate, at least try or ask me questions, so that I can encounter new questions from you guys. So it will be beneficial for me and as well as for other students also. And if you are having any problem, you please ask me. Don't hesitate.
I said, does
Yeah,
polymatrices
yeah.
does polymatrices comes changes in Hamiltonian?
Sorry.
Just we do in general solution.
Can you please repeat your
Sir,
question?
I
Yeah.
am asking. Yeah, sir, I'm asking that does the poly matrices comes does changes in the Hamiltonian? That means general Hamiltonian we do now.
I mean,
So
you
there
are.
is a question related to that.
There is another
Yes.
question related to that.
No, sir. The same question that you have told us, the corresponding to poly matrices. So
The
that point I
corresponding
didn't get. So
polymetric is so basically the polymetric in this question you are asking, right? Denote the corresponding polymetric, right?
yes, sir.
There's
Yes, yes,
a
yes.
that is not given because we I mean the polymetric for the x component, y component, z component that we know, right? That's the general thing you read in the for spin up particle, right? It obviously depends, if it is 3 by 2 spin 3 by 2 particles, it will change. Obviously, there will be 3 cross 3 matrix, but spin up particle, this is a 2 cross 2 matrix that we know, right? For what for electrons or protons, what will it be? I think you asked that question or you anything else?
Okay, sir. Yeah.
Yeah,
Yes.
yeah. Anyone else? Okay. If no one is asking me questions, then I will go to the next question. Okay, I am proceeding for the next question. Okay. Okay. So this question was also sent by Harish, but this is why I am discussing this question because in the I think 2 weeks back I discussed the same kind of question, but not exactly same. I found this question is very, I mean, little bit important. There you should know how to solve this kind of question. I mean, I think people can solve this. Anyway, I will be discussing this question. This question is from the CS and NET exam 2014. This question was asked. Also, similar type of question was asked in the GATE physics paper 2020 that I have already discussed. Anyway, I will be discussing this question also today. And so, okay, this question is the Hamiltonian H naught for a 3-state quantum system is given by the matrix H naught. That matrix is given by this 1 0 0 0 2 0 0 0 2. So this is the this is the primary Hamiltonian for the system, is the unperturbed Hamiltonian, right? Now it is given when perturbed by this Hamiltonian H dash equals to epsilon times 0 1 0 1 0 1 0 1 0, where epsilon is very less than 1. That's obvious because your perturbation should be small if you want to apply the perturbation theory. The resulting the resulting shift in the energy eigenvalue E naught equals to 2 is option A is epsilon comma 2 minus 2 epsilon, option B is minus epsilon comma 2 epsilon, option C is plus minus epsilon, and the last option D is plus minus 2 epsilon. Is the question is clear? Any doubt about the question? I
Quantum
mean,
Hamiltonian will give the resulting shift.
sorry.
Uh,
No, can you
I'm
please?
not sure.
No, you can tell. You are Amit, right?
Yes,
Hello.
sir.
Yeah, please tell me. Yeah.
Uh, yes, sir. So I'm saying that if we just find the eigenvalues of H dash, then it will give the answer, or it means something else. Means what is meant by the resulting shift?
Yeah, shift means, so E naught is the, so you can look into the subscript, right? Not, right? So H naught has the 3 eigenvalues. that you can easily find that eigenvalue will be 1, 2 and 2, right? This is a diagonal matrix, the H naught matrix I am saying.
Yes, sir.
There is the unperturbed matrix. So, but after applying the perturbation H dash, your eigenvalues will change because you are applying some perturbation. So, the 3 state will have some shift from the unperturbed value, right? But here you have degeneracy of 2 state because 2 state will have the same eigenvalue 2 in the unperturbed
Yes, sir.
condition. So, that question is asked here. The energy states having the energy eigenvalue E naught equals to 2, after perturbing this, what will be the shift? So, what will be the new energy eigenvalue minus your old eigenenergy value? That is the shift. You understood, right?
Yes, sir.
No, if you not clear, please ask me. Then I can tell it in another way. If it's not clear to you.
No, I'm just thinking, how can I approach this? I understood the thing,
Okay.
but how to approach the answer?
That's why I want to discuss this question, because last time I discussed a question, same thing, that your perturbed and unperturbed thing, you just add up and find the eigenvalues and just equate it with that. So this question is little bit different. I think Harish, that's why Harish sent me this question to discuss this, because the approach will be little bit different from that. Was here because it's a degeneracy involved in there. So yeah, okay, please try, then I will discuss the solution. So anyone?
So I just
Hmm.
considered H as means the total Hamiltonian after perturbation.
Hmm.
H as H not dash. Then I am trying to find its eigenvalues.
Okay, if okay, so if you find that eigenvalues from there, then how will you relate the three eigenvalues of the total Hamiltonian with the older? I mean, how will you find the shift then? Because you will get the three eigenvalues. That's correct, right? But how will you
Yes, sir.
relate to the older eigenvalues? Because that lambda void, you will get lambda 1, lambda 2, lambda 3, right? So you have to connect to the older
Yes.
eigenvalues 1, 2, 2. So how will you connect that? Because can you connect that to the things with the three eigenvalues of the H naught and three eigenvalues with the total Hamiltonian?
Or I can just apply the means how we find the first term correction
Right,
of
right, exactly. Here you have to use that, because last time you have
okay,
two
so I can
provisions. Yes,
find the eigenvalue,
yes,
eigenvectors,
yes. That's
and
the
then
thing.
sandwich the H dash in between that. Then I can find the values.
Exactly. That's why I am discussing with you. In this question, you have to apply the first order perturbation. because in the last time when someone, I think Sejal was there, she asked me if we are instead of applying the, I mean, if instead of considering the total Hamiltonian, if we apply the perturbation here, will you get the same answer? That answer was yes, but you have two provisions. You can directly go with the total Hamiltonian, or you can apply the perturbation theory with the corrected term. But here you have to apply the perturbation theory. You can't deal with the total Hamiltonian, because you can't relate the three eigenvalues. Also, you will get difficulty in solving the I mean total Hamiltonian determinant. What determinant you will get, secular determinant, because you will have a cube term. I think you can't easily solve that in that case. If you see that, I have
So, sir,
also,
I should take the eigenvector corresponding to lambda equals to 2 for
yes,
the H naught.
exactly. You have two desired eigenstates, right?
Yes.
Yes. For that,
Oh,
you find
so
the
for
part of
that,
yeah, yeah.
right?
Yes, for that you can
And then
find, you
I'll
can
find
find the
the
perturbed Hamiltonian for that two state only. Then
okay.
find the eigenvalues of the perturbed Hamiltonian, and then you will, that perturbed eigenvalue of the perturbed Hamiltonian will basically give you the correction term, that is the shift of your eigenvalue, right? You got my point, right?
Yes.
Yeah,
Yes, sir.
that's the procedure. I think people already listen to the to Amit's words. Please follow that thing. I will be discussing in that way only. So what will be the two states? Can you tell Amit for the eigenvalue 2, E naught equals to 2? Okay, let
Sir,
me
I'm
yeah, yeah. So let me cut this question into parts. Okay, first tell me, first find the eigenvalues and the corresponding eigenvectors of this unperturbed Hamiltonian H naught. Please tell me what are the eigenvalues and the corresponding eigenvectors. Please tell me this.
so the eigenvalues are just clear
Ah,
1, 2, and 2.
right. And the corresponding
Eigenvectors,
eigenstates for 1, for 2, and these two. Yeah.
I'm
Yeah,
calculating that.
yeah. Just find that and tell me. Hello.
Sir, is it C option?
Just give me 1 minute. Yeah. Please tell me. Yeah. Who's
Sir, is it C option?
who are you? Can you please tell your name?
Prajwal, sir.
Rajal. Okay. Okay. Before going to the correct answer, I want to ask you how did you solve that? I want to know the procedure.
So just find the vector
So, what the eigenvectors of this
which
H
is
naught? Can you please tell
corresponding
me?
to 0, 1, 1 and 1, 0, 0 for uh, for
Which
e, for e
we
equal to 1 is
equal
1,
E
0,
naught
0
equals
and
to
for
1,
e
you
equal to
found 001 or 100.
1, 0, 0 and
One, okay. And
for
for
2
other
it's
two,
0, 1, 1,
011 for both the two?
0, 1, 1. Huh.
That is not possible because there are three different states. So,
No, the
they,
other would be 0, 1, minus 1.
0,
1 minus 1.
0, 1 minus 1. Okay. So, you have to normalize that then 1 by root 2, 0, 1 minus 1, right? Okay. Then what
I
did you
guess.
do after that?
Just applied, just took the bra and get and
Huh.
put first order perturbation.
Then you find the perturbed Hamiltonian for these two degenerate states. You find the matrix
Sir, it is
element. Basically, you found the matrix element that is coming off diagonal term is epsilon and diagonal terms are 0. You are getting that, right? I mean,
yes, sir.
okay, okay, fine. Mm, okay, answer is correct. That will be plus minus epsilon. I think you have done the same thing. I mean, but okay, there are little bit thing I have to tell. I will discuss in the solution. Okay, okay. I will go to the solution then. Okay, just look into the solution part very carefully. The Hamiltonian for a three-state system is given by H naught, that is given in the question, and your perturbation term is epsilon times this matrix 0, 1, 0, 1, 0, 1 and 0, 1, 0, while epsilon is very, very less than 1. So, this is a three-state system. So, you will have three eigenvalues and three eigenvectors, corresponding eigenvectors. Okay. Uh, um, I will not solve this Hamiltonian to find the eigenvectors. You can check these things. You can get another eigenstate also. That doesn't matter. If you have done, if you have just found the eigen vector equation correctly. So you have, it depends on your choices because okay. So what I found for this Hamiltonian, you will get, that is obvious. The eigenvalues will be 1, 2, 2. For this one, I have chosen in such a way the eigenstate is 1, 0, 0. Okay. So the this thing will get 0, 1, 0, but for this 2 you will get the same equation, but your states should not be same. Okay. So if you just obtain these three things, and in this combination it will be easy to understand. If your first two state is along x axis, this y axis, then obviously third state will be along the z axis, right? So you have to just take the cross product. So this is the way to dissolve this problem in case of degeneracy when you are encountering the same state with the degenerate state. So is it clear this thing? You can,
Yes, sir.
yeah, I think this is a common thing we encounter in degeneracy problem. Okay. If you are not comfortable with this, you can ask me later. I will discuss this thing in a brief. Okay. So, so this is the three states, eigenstates and three eigenvalues of this unperturbed Hamiltonian. Here you can see the two eigenvalues are same. So, these two states are doubly degenerate states, right. Now, I will, so how we write the perturbed Hamiltonian? Basically, each of the term here, your matrix elements, right? And how we can get the matrix element, what is the general way that we are applying? There is a correction term here. So, first term is, so we will now deal with these two states phi 2 and phi 3, because these two states are the degenerate state having eigenvalues 2, and that has been answering the question, the shift in the energy eigenvalue 2, not 1. So, we will deal with these two states only. So, for the two states phi 2 and phi 3, your perturbed Hamiltonian will be this. So basically inner product between phi 2 phi 2, this will give you the first term in the matrix, phi 2 and phi 2 with this h dash sandwich between them, and here your matrix element with phi 2 h dash and phi 3, this will give you the 1 2 element. This is the 1 1 element, this is the 1 1 2 element, this is the 2 1 element, this is the 2 2 element. Okay, so in this way we can get the 4 elements. So we can construct the perturbed Hamiltonian for this state phi 2 and phi 3. So let us determine these terms now. So we know the h dash that is given in the question. You know the phi 2 is your 0 1 0 and phi 3 is your 0 0 1. So if you just want to find this this term matrix element, you will get 0. I have not shown the calculation. Okay. You can just multiply these two matrix first, then multiply with this matrix, you will get 0 essentially. For this term, you will get epsilon. For this term, we will get epsilon again, and for the for this term, you will get 0. Okay. So basically, your off diagonal terms are epsilon and diagonal terms are 0. So you essentially you will end up with this Hamiltonian 0 epsilon epsilon 0. So what I have done, I have found only the perturbed Hamiltonian for this involved in these two states phi 2 and phi 3. So you can see from the h dash Hamiltonian, you have this first two term 0 epsilon and epsilon 0, right. So basically this part of this matrix will give you the correction of this phi 2 and phi 3. So you have to confirm these things by in this way. So then we found the eigenvalues, that is if you just want to find the eigenvalues, you will get the plus minus epsilon. So the shift after perturbation, the energy will turn into 2 plus minus epsilon. So the correction or the shift in the energy eigenvalue 2 will be plus minus epsilon. So this is the option C. Is this clear to everyone?
Sir, I didn't understand the H5253.
You didn't get the point.
No, sir.
Okay. So okay. If you have a Hamiltonian in a matrix form, what does the matrix element signifies? Can you please tell me? You know these things when you want to okay, how can I say that thing? Okay,
Matrix formulation.
yes, the individual term is basically the inner product between these two state with that Hamiltonian,
Yes, I know that.
that you know, right?
Yes.
And Amit, I'm
But
not
what does this H5253 resembles actually?
sorry.
What does this Hamiltonian shows actually means this H5253?
Oh, this shows the part. This shows the perturbation involved for this phi 2 and phi 3 state. This is a correction of this phi 2 and phi 3 state. That's the significance of this Hamiltonian.
So, sir,
Yeah,
the single Hamiltonian will show the perturbation for both the states.
the single Hamiltonian means which Hamiltonian?
Means the single matrix
Hmm.
H5253 will. Okay,
This will
sir.
this is
What
this
if
this.
it was?
What if it was?
If we wanted to find for both phi 1, phi 2, phi 3, then the
Huh.
Hamiltonian would be.
Uh, Oh, okay. Then it will be, you have to construct in this way. So this will be, if you want to consider the phi 1, phi 2, phi 3, then it will start first 1 1, right? So phi 1 phi 1, then it will come phi 1 phi 2, then phi 1 so h 1 1 1 1 1 2 1 3, phi 1 1 3, then it will start from
Okay. Okay.
you know, right, the formation 1 1 1 2 1 3, then yes, that's thing you have to consider. But here we will not considering 3 cross 3 because we have to deal with the only two states here. That's why, right?
Okay, sir.
Okay, if you have any doubt, you can ask me later. It's okay. I'll go to the next one because I think I am running out of time. I have to discuss one more question. Okay, someone has. Okay, let me check the chat box. Okay, if someone has asked any
Sir,
question.
sir,
Yeah, yeah, yeah. I can hear.
sir, we have to find matrix with each column vector, na? Phi 2 and phi 3
Sorry, can you
in the
please repeat
next.
your question again? We have to find the each. Yeah, yeah, Aparna. Please tell me.
Matrix with each phi 1, phi 2, and phi 3.
5 1, 5 2,
Oh,
and 5 3.
we
Yeah,
have to
that.
find matrix with each phi 1, phi 2, phi 2, and phi 3, like that.
Yeah, that is you are saying.
Matrix and find the value, na?
Yeah, but here you don't have to deal with this phi 1 because it has eigenvalue e1. Okay, e1 equals to 1 because but in the question it is already asked you have to find the shift in the eigenvalue e naught equals to 2. So first see which states have the eigenvalue 2. Only two states, there are doubly degenerate states having the eigenvalue 2, right? So you don't have to consider this state now. So that will simplify your life. You can just deal with these two states now. So you can consider the 2 cross 2 matrix and deal with that. You don't have to consider the third, this state, first state here, because it has eigenvalue 1. That is not asked in the question. If you are asked the shift in all the three states, then you have to deal with all the three states that Amit already
So
have.
we need to
Yeah, yeah. Please tell me.
so we need to deal with h, sir. So we need to deal with h dash only
Yeah,
for
yeah, yeah.
finding the
Because
matrix.
correction, each dash will give you the correction, right?
Uh,
Each not is the primary Hamiltonian, that is the unperturbed Hamiltonian. So each dash will give you the
okay.
correction term, and if you want to find the correction term, what you will do? You do the that first order perturbation. What you do? You find the matrix element like this, right? Like this, right? Energy correction. And here I have formulated the matrix form because you have two states here. If you have one state, then you don't.
Yes. I, now it's clear.
Yeah, yeah. Okay, okay, fine. So I'll go for the last question of this class.
Okay, sir.
This is a very
Sir,
easy.
can you please show next slide?
Which slide? This slide?
Okay. Now clear.
You are asking for this slide?
Previous one.
Previous one. Okay. This one?
Previous slide. This
Okay.
one.
Okay.
Yeah.
Okay. Is it fine?
Now clear.
Yeah.
Clear, sir.
Someone want to ask the question?
So actually, I asked Harish, but he said that the correct option is D option.
Option D. The option D is.
Means he posted this question in Telegram, but I tried and he said that answer is D.
Plus minus 2 epsilon. Okay. Okay. How can. But okay, I will check the answer for the CSR NET 2014. Okay. Then I have to confirm. But I don't think so. Why did I do any mistake? This is the way. So Harish has solved the question already. Hello. Am I audible? Am I
Yes,
audible?
So you're working
yes.
a little.
Yeah, yeah. Now, can you hear me? Hello.
Yes, sir.
Okay. So, Harish has sent
Yes, sir.
the.
Now you are audible.
Okay, okay. Harish has sent the solution in the group. I mean, I'm not aware of that. I mean, if you have the he has a solution, then I can see the solution. But I don't
No,
think.
sir, not in group, but I asked him in the.
Okay, okay. Okay, then just I will
Sir,
check
not he
the
has not sent,
answer.
but
Okay, I'll check the answer key for this 2014. Okay, then this so that I have not checked, so that I can confirm, it can be confirmed, because I don't think there is any mistake. I'll check. Okay, okay. I can't find why it should be plus minus 2 epsilon. There are two terms why I am missing. I'll check. Okay. What's your name, by the way? Hello. Prajul. Okay. Okay. I'll check and I'll confirm the next class. Okay. I have to check then.
okay.
Okay. Okay. Fine. Okay, fine. So this is the last question for our. Okay, so what I have shown, please, I mean, sit with the question after this class. If you find anything steps mistake, I have done any mistakes in that, please inform me in the next class. Okay. But I can't see any mistakes in the solution.
So
Maybe,
I'll
yeah.
also check with other eigenstates, means 0, 1, 1 and 0, 1, -1. I'll
Okay.
try with that if the
Try.
answer comes.
Okay, just try that. Okay. Mm-hmm.
No, sir.
Okay.
With that eigenstates only, I got plus minus epsilon.
Okay, okay. You got plus minus one with that
Okay.
also. I think it will not change anything, because minus
Yes, sir.
sign, basically you are multiplying a minus sign with that state 0, 1, 1, 0, 0, 1, right? That will not change your story. That's the thing. Okay. If you multiply a constant term with your eigenstate, that will basically your change your normalization term, or that's the thing. Minus sign will not change your answer here. Okay. uh, okay, I'll check the answer for this question.
Okay, sir.
Okay, if it is, I mean, okay, fine. So this is the last question of our class. So I want you guys to tell me the answer very quickly, because this is a very straightforward question from solid state physics. So the question is, this question is asked from in the gate physics paper 2020. This is the numeric answer type question, 2 marks, having 2 marks from solid state physics. The question is, consider a simple cubic monoatomic Gravius lattice which has a basis with vectors r1 equals to 0 and r2 equals to a by 4 times x cap plus y cap plus z cap, where a is the lattice parameter. The Bragg reflection is observed due to change in the wave vector between the incident and the scattered beam as given by k vector equals to n1 times g1 vector plus n2 times g2 vector plus n3 times g3 vector, where g1 vector, g2 vector and g3 vector are primitive reciprocal lattice vectors. So it has been asked for n1 equals to 3, n2 equals to 3 and n3 equals to 2. The geometrical structure factor is dash. So you have to find the geometrical structure factor for this n1, n2 and n3 value. So anyone can anyone tell me what is geometrical structure factor? You should know this. You have did this thing in the X-ray diffraction chapter. Anyone? Amit? Aparna? Anyone?
So it was
Yeah.
summation over exponential times twice by I times
Uh, uh,
something I don't remember.
okay. No, so you don't have to tell me the terms.
Sir,
Yeah. What does it physically mean? Geometrical stuff. What
su-
will it give? Yeah. Yeah, Aparna.
summation over e to the power
Hmm.
2 pi iota
Hmm.
UGH plus
Hmm.
VJK plus WJL.
Right.
Uh,
Right. So here each scale are the Miller indices. You know that related to plane, and UJ, VJ, and WJ are what? That are the
HKL are Miller indices.
and UJ, VJ, and WJ are.
Uh,
Hello.
uh,
Am I audible? I can't hear properly. I don't know.
Yes, sir, you are.
Yeah, okay. So that's the fractional coordinates of the basis, right?
Yes, sir, you're
Hello? Hello?
yes,
Yeah, can you hear me, Aparna?
yes, sir.
Okay, fine. So what does it physically mean? And the geometrical structure factor.
The ratio of the amplitude of scattered and the one which is incident,
Right. So basically,
which changes due to
this
the
will
geometry of.
yes, exactly. So basically, it will give
Ratio
you,
of action
huh? Yeah.
by amplitude.
Yes. Basically, so after scattering, you have different scatter or different basis, you can say. What portion of the incident rays will be scattered, that will be given by this geometrical structure factor, right? So that's the ratio what you have said. So what ratio will be scattered from this scatter of this crystal? That's the thing. So okay, so you know the formula for the geometrical structure factor. You have everything in this question now. You have to just apply the things in the structure factor and apply, then put the N1 into an entry value. So let me give you the simplify these things. Here N1 into N3, it is given by N1 into N3. These are basically related to Miller indices. This is similar to HKL. So you can consider it as HKL, and this G1, G2, G3, these are the A star, B star, C star. It has been represented here by G1, G2, G3, but these are the same. Okay. So now I think it is clear to everyone. You have two bases now. So you have two basis point. So you know how you just try to put the points and find the geometrical structure factor and then put the N1 into entry value. That's the thing. So any doubt after that? I have told all the things what you have to do here. Aparna, you got it right. I mean, what you have to do here?
So, sir,
Yeah.
yeah, I substituted the values.
Okay.
Then finally I got 2 as answer.
Yes, the answer is two. This is too simple. This is a question is simple. That's why I told the question is simple. You have to know.
Just substituting
Yes.
values.
Yes. That's the thing. So
1 plus e to the power 4 pi
4 pi
iota.
I. Yeah.
That we simplify.
Yes, 1 plus 1, that is 2. The answer is 2. That's correct. Okay, I'll go quickly to the solution. I think this is a very straightforward question. So I don't have to discuss much. Okay, for a simple cubic monoatomic Grievous lattice which has two bases, that is 0 and at 0 and at a by 4 comma times x cap plus y cap plus z cap. Here is the lattice parameter. So the basis atoms are lying at 0, 0, 0 and 1 by 4, 1 by 4, 1 by 4. That you understood from these positions, right? So according to the question, this k vector, this is a capital K vector, is basically your difference between two k vectors. So this is the incident K vector, this is the reflected K vector. So we can from the Edward construction, we know that this reflection will happen when this is the linear combination of your reciprocal lattice vectors, that is n1 times g1 vector plus n2 times g2 vector plus n3 times g3 vector. So here n1 into n3 are basically analogous to Miller indices. Here it has been represented by n1 into n3, and g1, g2, g3 are primitive translation vectors in reciprocal space. Basically, those are the primitive reciprocal vectors. That can be, we usually write it as A star, B star, C star. Okay, fine. Now geometrical structure factor for n1 into n3 is expressed by in this way, that already Aparna has said, or all of you know, I think. So that is S as a function of n1 into n3 equals to summation over j exponential of 2 pi iota times xj times n1 plus yj times n2 plus zj times n2. So the number of bases you have to run the summation over that. Okay. So here you have two bases, so it will run over j equals to 1 and 2. So for j equals to 1 you have this basis, j equals to 2 you have this basis. So these are the values of xj, yj and zj. Okay. So x1 y1 z1 you have 0 comma 0 comma 0, and x2 y2 z2 you have 1 by 4 comma 1 by 4 comma 1 by 4. And so you just put these values for j equals to 1 and 2, you will get exponential of 2 pi I times 0. This will give you 0 because all that xj yj is 0, and this will give you in 1 by 4, in 2 by 4 and in 3 by 4. So eventually you will end up with exponential of 0, that will give you 1, and the second term is exponential of 2 pi I by 4 times n1 plus n2 plus n3. So this will give you exponential of pi I by 2 times n1 plus n2 plus n3. Now for n1 equals to 3, n2 equals to 3 and n3 equals to 2, the geometrical structure factor is, so you just put the values here. So it will give 3 plus 3 plus 2, this will give you 8. So eventually you will get 1 plus, here it will give exponential of 4 pi I. Now you know exponential of integral multiple of 2 pi I will give you 1. So this term will give you 1. So it will be 1 plus 1 2. The geometrical structure factor for this crystal structure will be 2 for this given n1, n2 and n3 values. Is this clear to everyone? This was very straightforward, formula based. You have to just identify the basis that is already given in the question. Is
Yes,
this,
sir.
yeah, okay. Okay, so I think one confusion already raised by Prajwal, so I will check that this question, right? The option Harish said the option D is correct. I'll ask him personally why did he got this, how did he get this solution. I mean, if he had the solution, then I can ask for that, or I'll check the answer key for this year's and December 2014. Okay, fine.
Okay.
Okay, there. So today time is left. Also, I could not get timer. So there are 2-3 question was asked last time, and Amit, I could seriously I could not get time. I'll check. I'll check the EM
It's
questions.
okay, sir.
Okay.
So,
Yeah.
from today's question, I have from this question only, I have another doubt.
Which question? This question? Yeah.
So, this one. Yes. So
Oh.
in this question, we solved it by taking only the H dash, and in the previous class, we solved another one where we considered the total
Total
Hamiltonian.
Hamiltonian.
So, what was the difference
Okay,
actually?
the question was different. So that's okay. I'll open the PPT. Okay, for you. Just give me a minute, so I can
Okay.
show you the question also, previous question. Just give me a minute. Okay. I think that was 2 weeks back. I think week 5 question was there. Let me check. That question was this. Okay, I found the question. Okay, I am sharing my screen. You can check the question now. Okay, the question was little bit different here.
Okay.
Okay, just see the question now. This was the question, right? This was the question, right? We are talking about in the week 5 class, 2 weeks back.
Yes, sir.
So in this question, you can see the maximum energy eigenvalue of H cap. So it has been already said the eigenvalue of the H cap. So this is the you have to find the eigenvalue of the H cap here from here. So that's why you are dealing with this, because you have to deal with the eigenvalue of H cap here.
Okay.
But in this question, you have to find the shift of the unperturbed Hamiltonian. So you have to deal with the perturbed Hamiltonian. That will give you the shift. The question is a little bit different here. So in this that thing will work
Okay.
here if you both the things will work here. Okay, because in this particular question both the thing will work. Either you can apply you can find the eigenvalues for total Hamiltonian, or you can just find the the energy eigenvalue for the H naught is E. So you can find the individually corrected terms. You can apply the perturbation theory here. So both the thing will work here. But in the other question, you have to specifically deal with the perturbation, because you are not asked the total energy eigenvalue in this question, right? So that's the difference of this question. That's why I
Yeah.
wanted to discuss this question. I mean, when you will be asked to shift in the energy, it's better to deal with the perturbation. That's the thing. Okay.
Okay, got it. Yeah.
Yeah, yeah. Okay. Then I think in the last question you have no doubts. Anyone? Okay. Then thank you guys. So there are
Thank you, sir.
some just don't leave. I have to
Thank
take.
you, sir.
Just don't leave. One thing I want to mention. I think everyone is old students or someone has joined for the first time. Anyone? I think everyone has joined in the Alekes. Okay, fine then. Okay, thank you guys.
Okay, thank you, sir.
Thank you. Yeah,
Thank you, sir.
thank you. Okay, it's done.